Mi senti se si sente bene? Forse è troppo alto il volume? Non si sente? Pronto, 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 pronto. Ma si sente bene o si sente perché parleranno a una distanza maggiore? Alzi il volume. Senti se si sente bene. Hello? Prova, 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 prova. Prova, 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 prova. Now there is?
椅子がつくね。いい。
Advance the slide, so
だからこれからデータを提供するんですけど、まあいいや。 ね、全部省いちゃってきめ2つ入れちゃうんだから、usati sia origine.
I'm afraid it's not long enough for your position. Altogether, it would be good
space studies in New York City.
All good? All good. All good. Okay. You need to. I'm sorry? Yeah.
Can we use that?
For the questions.
Like, it's hard for us, the microphone's so far. Yeah, is it okay? Okay.
It's too short.
I mean, because it just, when we talk, because it's hard to reach this microphone.
Yeah, no, that's
Yeah.
fine. I'll
So
do
maybe
it. I'll have
she
it,
can
yeah.
use it and...
Yeah.
Yeah, please give it to me.
Right. Sorry, we're doing future generation as well. To be from the end.
I think for you it's fine. Maybe she lets me use that. Because it's too far.
Okay. Hello, I'm Anita Hewitt. I am the press officer for the European Planetary Science Congress, and I'm delighted to welcome you to this, our final press briefing from the European Planetary Science Congress joint meeting with the Division of Planetary Sciences in Geneva this week. With me, we have Shantanu Naidu, who's the DPS press officer, and my colleague, Livia Giacomini, who has been doing an amazing job with the live streaming all week under very stressful circumstances. So thank you so much, Livia. We really appreciate your efforts. Today, we have a really packed briefing. We have 6 speakers who will be talking about various aspects of Venus. We have 3 distinguished guests from the Akatsuki mission. We have the project manager, Masato Nakamura from JAXA, the Japanese Space Agency. We also have Takeshi Horanuchi from Hokkaido University, and we have Takeshi Imamura from the University of Tokyo. Following that, we will be moving on to look at a campaign of joint observations of Venus in 2020, when the Bepi-Colombo mission will be flying close to the planet Mercury on its way to, close to the planet Venus on the way to Mercury. And we have Valeria Mangono, who will be telling us a bit about Bepi-Colombo and what it will be doing, and then Yuan-Ju Lee from the Technical University in Berlin, who will be talking more generally about the campaign of observations. And finally, we have Michael Way from NASA's Goddard Space Science Institute, Institute for Space Studies, who will be talking about whether Venus itself might have been habitable sometime in its past. So I will hand over now to Masato Nakamura, who will start today's press briefing. Thank you.
So let me start with the introduction of the Akatsuki mission. Akatsuki is the Japanese Venus climate orbiter, and it was planned in 2001, and we built it for 10 years. We launched it in 2010 and arrived at Venus in 2015. And since then, we have been observing Venus with 5 cameras. What we are interested in is the difference between the Earth and Venus atmosphere. The mission goal is to understand the Venusian atmospheric dynamics and characteristics, which is quite different from that of the Earth. Especially, the atmosphere rotates 60 times faster than the planet itself. That never happens on the Earth. So the most important question is, why does the Venusian atmosphere rotates much faster than the planet itself? How is this flow maintained? This first zonal flow is called superrotation. And the superrotation direction is westwards. So we chose Akatsuki's orbit as equatorial westward orbit to take motion pictures of Venus to understand the dynamics of atmosphere. And we have 5 cameras, IR1 and IR2 are 1 micron and 2 micron near-infrared camera. LIR is the mid-infrared camera. The wavelength is 8 to 12 micrometers. And we have UV imager, which detects the SO2 and unknown observer distributed at the cloud top. And LSE is a lightning detector, and we have another science using the radio occultation, that is the transmitted radio wave from Akatsuki is detected on the ground, and when the wave is transmitting through the atmosphere, then we will understand the vertical structure of the atmosphere. Then with these observations, we clarify the 3D structure of the Venusian atmosphere to deepen our knowledge of meteorology. We launched Akatsuki in 2010, and we expected to insert it into the orbit in December 2010, but we failed it. And the main engine got broken during 2010 Venus orbit insertion due to a faulty check valve in the fuel line. And oxidizer-rich and fuel-poor condition resulted excessively high temperature as the orbital maneuver engine, and it was broken. And the Akatsuki was again put into the orbit around Sun, and we had another 5 years to have the next chance. The 2015 VOR return was performed by combining 4 reaction control system thrusters located on the top panel. And we had a 20 minutes burn of the reaction control system. And this time we successfully inserted the spacecraft into the orbit. The periapsis is a little bit larger than the expected, but we have been observing Venus since then. So this is the example images taken by each camera. This is the first one is IR1 and UVI, and this is a synthesized fourth color image. And the famous Y-shaped structure is clearly seen on this picture. This is cloud top image, and on the other hand, when we see the deep cloud layer, this is Venus night side clouds taken by IR2, very much different from the left side cloud top layer. And the last camera is the LIR, and this is the cloud top temperature taken by LIR, and we see a huge bowl-shaped structure, and this is not what we have expected. So Takeshi Imamura and Takeshi Horinouchi will present the topics of the today's Venus session, and okay, this is the thermography of clouds presented by Fukuya, but he will explain it.
Okay, I'm Imamura, and this study was mostly done by one of my students, Mr. Fukuya, who is sitting there. And in this study, we tried to obtain several key parameters using thermal infrared camera on board Akatsuki. And the main results are summarized here. First, we visualized the detailed morphology of the cloud top temperature distribution for the first time. And the next, we through this analysis, through this study, we established a new method to see the night side of Venus cloud, and we opened up the possibility to measure the atmospheric motions at all local times. This is quite new result. The analysis procedure is like this. The original image is quite flat. We cannot see notable features. And even after so-called high-pass filtering, the image is dominated by small-scale noise, so we hardly see notable cloud features. I forgot to say that seeing small-scale cloud features is quite important to understand the dynamics of the atmosphere, especially inside clouds, which sustain the superrotation and maintains the sulfuric acid clouds. But in this high-pass filtered image, we cannot see interesting features. But we developed a new method to reduce the noise. We averaged multiple images to reduce noise. But simple averaging smoothes out not interesting features also. So therefore, we averaged images in the coordinate system moving with the background wind. Then we can extract small-scale cloud features which are advected by the background wind. The some of the results are shown here. In the top panel on the right-hand side, we can see small-scale mottled or turbulent features, and on the lower panels we can see spiral features, and we can also see streaky features. And these features indicate. I forgot to say that the bright region corresponds to warm cloud, and dark regions correspond to cold clouds. And we currently do not know what produces these features, but these complicated structures should reflect unknown dynamics in the cloud. And this method also allows us to sense the dynamics of the atmosphere, including the night side. Up to now, we know that rather strong poleward circulation exists on the dayside cloud, and but it is still unknown whether this strong poleward circulation, exists also on the night side, and there is a very strong Hadley circulation, something like this, or this poleward circulation is compensated by the equatorward circulation on the night side. This is a long-lasting mystery or big question in the Venus atmosphere science. And the analysis is still ongoing, but some preliminary results are shown here. On the day side, we can see strong poleward circulation in the newly obtained thermal images. And you can see expanding cloud motion in the equatorial region. But on the night side, you can see strong equatorward motion, and you can see rather shrinking tendency in the equatorial region. And of course, we have to collect more data, and very careful statistical analysis is needed. But now we can say that we can start to understand the local time dependence of the Venus atmosphere dynamics, and we are approaching the full understanding of the large-scale circulation, mean circulation of the atmosphere. And we can also say that this kind of day-night contrast of the cloud motion will be associated with so-called thermal tide, which is a planetary scale wave excited by strong solar heating of the cloud layer. And this thermal tide can transport angular momentum in the atmosphere to maintain the strong superrotation. This study is also ongoing. Thank you very much.
Thank you. Okay. So I'm doing cloud tracking, and we used a novel automated method with sophisticated error correction and quality control. So can you go to the next slide? So this figure shows an example of our results. And in this case, the background wind, super rotating background wind, and also the thermal tide treated by Imamura-san has already been subtracted. So this figure shows only a small residual from this background. And if you are familiar with, for those who are familiar with Venus cloud tracking, this figure itself is a very surprising and amazing one. Even though we showed small residuals, but it suggests it includes a whole lot of whole variety of motions, like planetary scale waves. So, for example, if you look at the top panel, then I should. Yeah. So in the middle, the wind is moving to the west, and the rest is the wind moving to the east, suggesting that the planetary scale wave existing, zonal wave number 1, so the eastward in one hemisphere and westward in the other hemisphere. And also, this figure shows some turbulent motions, which is newly discovered, and that is made available only with our novel technique, and also, of course, the good quality of Akatsuki data. This figure shows the mean wind, the one that have already been subtracted in a previous figure. And the 5 panels shows the mean winds, actually in this case, the westward wind for different sub-periods over 3 years, so each containing 7 months or so. So in the second sub-period, middle top panel exhibits some significant north-south asymmetry. So in the southern hemisphere, the wind was fast, and in the northern hemisphere, wind was slow. Also, the wind varies time by time, and if we only have this measurement, then we may conclude that there is actually a big asymmetry in the second sub-period. However, fortunately, we have another filter which is takes images at slightly different wavelengths. And in this case, the second panel, the second period, is more symmetric. So what's the difference? First of all, these are the derived from ultraviolet images, and there is some absorbers of ultraviolet sunlight. So, and this absorption is provided by a so-called unknown UV absorber. So it's kind of surprising that the existence of the absorber has been long known for over 40 years or so, but still we don't know what it is. However, and also at this wavelength, the absorption occurs at SO2. That's a known features. And the comparison actually suggests that, that the difference in or the north, what appears to be a north-south asymmetry may be due to the difference in the vertical distribution of unknown absorber and SO2. So this gives us interesting questions on the distribution of the chemical substances and their interaction with a mean wind. So then I finish.
Yeah. Sorry.
So, okay. So there will be a moment next year in which Akatsuki will not be left alone orbiting around Venus, because there will be Bepi Colombo, the joint ESA-JAXA mission that was launched last October, successfully launched last October, on his way to Mercury, that will pass close to Venus. We'll make a flyby. The first of two will be next year, and this was the idea. It raised the idea to plan a coordinated Venus observation of Bepi Colombo just passing, with Akatsuki being there and making his observation, and hopefully also ground-based observation by terrestrial telescopes. So we now tell a little bit about this, and I will tell you something more about Bepi Colombo in case you don't know already. So Bepi Colombo is made of two different spacecraft that are called Mercury Magnetospheric Orbiter, and this is the Japanese one that after launch was renamed MIO. And then we have the Mercury Planetary Orbiter. In the image that you see on my back, MMO is inside the white shield that it's a sound shield and is built to protect it during the cruise. MPO is the red one, and as you can see, they are packed together with a fourth part that is MTM, the transfer module that has the engine that is driving the two spacecraft to Mercury. So this is the cruise configuration, and this will allow the instruments to stay safe. And originally it was not planned to have some science, but on the way to the launch, it was believed that for Bepi Colombo will make one flyby at the Earth, 2 at Venus, and 6 at Mercury. It was probably really worth to make also some science, and for Venus will be, it's very close. And in particular, to coordinate with the Akatsuki, Mertis and Phoebus, which are two of the instruments on board MPO, will be able to give a remarkable contribution, hopefully. So consider that on board MPO we have 11 instruments, or suite of instruments, and 8 of them will be able to operate. Because they will be on the side, so not shielded by the MO on top or by the transfer module on the back side, and will give contribution to the atmosphere, as it will be said by my colleague now, and also to the induced magnetosphere and all the plasma environment, because many instruments are dealing with are detectors of electron, ions, and there are magnetometers on board. Something similar will happen on board the magnetospheric orbiter, because 3 of 5 instruments will be able to operate, and for this is a magnetospheric orbiter. Of course, the bigger part will be given by a bigger contribution can be done on the magnetosphere and plasma environment side, but also the outer part of the atmosphere, the very tenuous outermost part of the atmosphere called exosphere, will probably be investigated as well. About 2 flybys. The first one will be about 10,000 kilometers of altitude, so not that close, but in any case much closer than the orbit of Akatsuki. And the second one instead is will be only 1,000 kilometers, but hopefully also very it will be also reduced, so very close to the planet. And I think that's all.
Yeah, thank you very much. So here, from here I will continue. Yeah. Seems fine. Thank you. Yeah, so this figure shows the expected trajectory of Baby Colombo and Venus and Earth. And at the time of the closest approach is shown in the left diagram. So blue is Baby Colombo's Venus flyby, and red dot shows the closest approaching time. And at the time, Akatsuki will be shown in the lower part, red dot. The black curve is Akatsuki's orbital trajectory, and the near apocenter that Akatsuki will be able to see Venus together with Baby Colombo. So as you can see from this image, the viewing direction to Venus from the Baby Colombo and Akatsuki will be overlapped, and the Earth will be the other side of the planet, so we'll be able to cover the morning side, during which we will not be able to observe by the spacecraft. So it can be a very good opportunity to cover morning time and the afternoon time together. So this diagram shows that how Venus would be look like from the Earth, the left figure, and the Venus seen from the Sun shown in the middle figure. So this figure shows that how the Venus would be look like from the Earth. Then let's continue how it would be look like using that at the position of the Baby Colombo and Akatsuki, the Earth. So this animation shows the Venus as seen from these 3 observing points, and the left one shows that the rightmost one shows the Earth view, and we can see that mostly it will cover morning side. The background image shows the LIR images, but we expected we would see some similar features using this the instruments at the mid-infrared range. And the morning side is covered by Earth observations, and Akatsuki the time will observe the evening terminator half illuminating condition. And the Baby Colombo, as you can see during the Venus flyby, it will change the local time very quickly, starting from around late afternoon, close over the noon time, and then it will observe until the evening terminator by Metis. And we expect we will make collaborative observations with ground-based observations. For example, Canada, France, Hawaii telescope facilities shown in the top panel, and NASA's IRTF telescope facility. These 2 telescopes we are discussing to use these 2 telescopes for these coordinated observations. And another instrument, that the UV spectrometer coordination, is under discussion between the PHIBOS and the UVI. So the PHIBOS case will make Venus observations during approaching phase. So before closest approach, like 1 or 2 months before the closest approach, it will start Venus observation for 10 days. So this plot shows that again the Baby Colombo's trajectory in blue curve, and the left close-up image shows the Akatsuki's trajectory. So during the time of the approaching, that the red dot is the location of the 2 spacecraft. During its approaching phase, when Baby Colombo is approaching to Venus, Akatsuki will be able to cover day side very nicely. So this data set perhaps can be compared for the same time and the same phase angle. So it will be a very useful data set to validate observations each other. So last image is shows how is the observational condition during the second flyby. So it's under discussion yet, but you can enjoy how it will look like at the time of the second Venus flyby.
Hello, my name is Michael Way from the NASA Governance for Space Studies. I'm going to take you from experiment, which you just heard, some excellent results from Akatsuki and what will come from Bepi Colombo, to much more theoretical calculations that we've been doing in my institute for the past several years. There has been some theories around for quite a number of years that Venus might have had liquid water on its surface, and we have some observational evidence that there are granitic compounds and such on the surface yet to be confirmed. So we've been doing a series of simulations that assume that Venus would have a rotation rate very similar to what it has today throughout most of its history, and that it did have surface liquid water in its early history. When we combine those in a three-dimensional general circulation model, which we call Raki 3D, it's a model developed at our institute in New York City, we then give the planet some different kinds of atmospheres and different kinds of topographies, because we know that Earth today does not have the same topography it had 4 billion years ago, and it's unlikely that Venus also had the same topography 4 billion years ago as it has today. So we do a set of simulations with different sorts of topographies, different land, sea masks, different amounts of surface waters at each of the points you see here. So you can see there's a large error bar shown at 4.2 billion years ago, and another one at 1 billion years ago, and yet another one basically today. Now, we don't know the very early history of Venus very well. We don't know the longevity of its initial magma ocean, which is very important for understanding its outgassing history and whether it actually had water on its surface, condensable water on its surface or not. But those are calculations that will continue, and we need more missions to Venus to confirm what those are saying to us. But the first set of simulations are mimicking what we believe happened on early Earth. So we believe that early Earth probably had a mostly CO2-dominated atmosphere of roughly 1 bar, roughly what we have today. And what you can see here is that at 4.2 gigayears ago, that Venus already, with surface liquid water, would have had temperatures ranging from roughly between 25 and about 45 degrees centigrade. That's the global average surface temperature. And that's with a 1 bar CO2-dominated atmosphere. Then as we go on in time, we believe that Venus probably would have had subductive plate tectonics. We know that there's a lot of evidence now for Earth having subductive plate tectonics very early on from zircon data. And we also know that the accretion history of Earth has been dropping off very quickly in its early history, if you read recent work by Stephen Mogis and collaborators. So as time, the planet has a carbon and silicate cycle. That CO2 is drawn down. We end up with more nitrogen in our atmosphere. Basically the same thing that's happened to Earth. So we rely upon comparative climatology and comparative planetology for understanding early Venus's history. And then until about 1 gigayear ago, 1 billion years ago, we then do another set of simulations where we have an N2-dominated atmosphere, which is nitrogen-dominated atmosphere, very similar to what Earth has today. And again, you can see that for the range of simulations we've done with different topographies and land, sea masks, that we have a range of temperatures, again, running from around 20 degrees to 40 degrees centigrade for the global surface temperature. Now, we've done another set of simulations with today's insolation, and you can see at the very bottom of the picture that at 4.2 billion years ago, the insolation that Venus receives is about 1.4 times what Earth receives today. So about 40% more sun was reaching Venus as Earth receives today. At about 1 billion years ago, it was about 1.7, and today Venus receives almost twice the solar insolation. But I think what's a bit surprising is that even today, if Venus had liquid oceans and had a 1 bar nitrogen-dominated atmosphere as Earth has today, it still would have had surface temperatures amenable to having surface liquid water on its surface. But we don't see that today, of course. What we see on Venus today is an incredibly hellish world with temperatures over 500 degrees centigrade. So what we believe is that something has happened between roughly 1 billion years ago, or maybe a bit early before that, and today. And we see that on the surface of Venus. We know that roughly 80% of the surface of Venus is new. It's been resurfaced by huge amounts of outgassing of some sort that has made the surface quite new. We know that from crater counts on the surface. And so what we hypothesize in the paper that come out later this fall is that probably large-scale, large igneous provinces were begun on the surface for reasons that we don't quite understand yet, which we have seen on Earth. We have seen on Earth large igneous provinces like the Siberian traps and the Deccan traps, which are correlated with very large mass extinctions on Earth. And we believe that outgassing events similar to those would have basically released most of the carbon dioxide locked up in carbonates in the crust of Venus, like we see on Earth today, and all that carbon dioxide ends up in the atmosphere of Venus. And it turns out the carbon dioxide budgets for Venus in its atmosphere and Earth locked up in its crust are roughly the same. So this kind of goes along with those calculations. So again, we believe that Venus probably could have had a habitable surface liquid water conditions for basically most of its history, and that something has happened in the last billion years that has completely driven the climate into a completely different state. Thank you very much.
Thank you to all our speakers for very interesting presentations. Do we have questions from people here in the room or online? No, you've been. Yes, here we go. Right. Can you say your name?
Hans-Arthur Masiske, Heise Online Germany. I've seen you're using global climate models for understanding Venus. Do you think you can improve these models applied to Earth by using the Venus data, or what's the influences between climate modeling on Venus and Earth?
Just say quickly, our model is derived from an Earth climate model, and we have a lot more data for Earth than we do for Venus. So the most that we can do is we can push the model into physical regimes that we don't normally encounter on Earth, and that tests the physics that's coded in the model. And in that sense, we have improved the Earth climate model to some degree. But that's really the extent. We have so much more data for Earth, we have so much more detailed observations that it's hard for us to improve Earth models very much. What we really need, though, to improve our models for Venus, I think we will all agree on this table, is more missions to Venus, back to the surface, and mapping missions, which the Envision mission, of course, which will be discussed tomorrow to some degree, will also help us.
Oh, I can make a comment to his. Okay. As for that problem, the observation of the current Venus will also contribute. I mean, as I understand, the habitability of early Venus depends on the atmospheric circulation regime. So the condition of the development of superrotation should be understood. And from this viewpoint, the understanding of the current atmospheric dynamics of Venus using data, for example, from Akatsuki, should contribute to such understanding, as I understand.
Thomas Schumann, I'm a freelance journalist from Denmark. I have a question regarding the carbonaceous rocks. As far as I've understood, that's a source of the high level of CO2 in the atmosphere on Venus. I just want to make sure that I've understood that correctly.
Yes, that's correct.
And that gets released at a critical point when the planet heats up. Is that also correctly understood?
It gets released at a critical point when the planet begins the resurfacing process that we see the results of today.
So that means that volcanism in this case would be involved in releasing this carbon into the atmosphere?
Absolutely. It would be what we would call intrusive volcanism in the geology community. Could I ask the Akatsuki team a question? So you were talking about the UV absorber and how there was some asymmetry in your profiles. I couldn't tell how asymmetric the data was, but Venus does have a small obliquity. Do you think that could play some small role in what you're seeing?
Well, I do not think that affected what we observed, because the asymmetry varies significantly over short time, and obliquity, of course, not.
Does not, yes.
Since the graphic is still there, I was wondering, how do you know that there was nitrogen in Venus' atmosphere, or is it just a hypothesis?
No, because Venus has almost 4 times as much nitrogen in its atmosphere as Earth does by bulk weight.
Yeah, the Venus atmosphere is very thick, so the total amount of nitrogen is not small. It is larger than the Earth.
Sorry?
But I mean, the total amount of nitrogen in the Venus atmosphere is
It's about 4 times as much.
4
bulk
times.
weight,
Okay, yeah.
If you compare it by
Yeah.
bulk weight of the planets.
Right. Are there any further questions? In that case, thank you very much for coming today. Thank you very much for tuning into the webcasts of these press conferences. Our next European Planetary Science Congress will be in Granada, in Spain, in late September, 27th of September to the 2nd of October 2020. So from Geneva, thank you very much, and we look forward to seeing you next year.
Thank you.